I made this video to help with questions that came up in Lab 10 regarding how to solve Part A, or how to address Part A of the assignment. In Part A, we're trying to solve this equation 1 by a matrix method, and as explained in the handout that was posted on heat transfer by the matrix method, that document was posted on the Moodle site. We take this equation and we create a matrix which has the form A times T is equal to B. And that matrix, the formation of that matrix is the focus of the assignment. That along with forming the vector B and then solving for the temperatures. The calculation of the temperature, once we got the matrix A formed, take the inverse of A multiplied by B, that gives us the temperatures. And I asked you to set this up for the case that's shown here with L equal to 0.5, TL equal to 100, TR is equal to 20, K is equal to 0.5, and then for 4 different values of Q. I'm going to show some background on this, and then I'll go through the procedures in MATLAB that are used to solve this. So the handout that gives the background on the formation of the matrix was posted on the website. The equation, which is a second order ordinary differential equation, is given here. This equation applies to, or can be applied to, the case that's shown here, a wall with temperature specified TL on the left-hand side, temperature TR on the right-hand side, and we have some sort of heat generation or heat extraction going on inside the wall. There is an analytical solution for this equation, and that's given here. It's a second order polynomial, and we can see that depending on the value of Q, if Q is equal to 0, we get this straight line distribution of temperature in the wall. If Q is positive, then we get a bump up, and if it's negative, we get a bump, or we get this depression below for the temperature distribution. All right. So solving this with the matrix method, that was done, what I just showed was for analytical solution, basically integrating the equation twice. But instead of integrating it analytically, we solve it numerically by converting this equation into a set of algebraic equations. And here I show the case where the wall is divided into 9 equal grid cells. But we could use as many as you like. There's a minimum number that's required, but we could have 10,000 grid cells. And what I want to do is to show you how you can set such a thing up and solve it by writing some script in the script command window, or we could do it also in the main command window of MATLAB. So taking the differential equation and replacing the derivative by an algebraic expression that's shown here, and the right hand side is just the ratio of Q over K, which is just the heat generation rate Q in grid cell I divided by the thermal conductivity of grid cell I. In our application, we're going to keep those values the same for all grid cells. The algebraic equations, or the transformation of the derivative and use of that transformation in the equation that we're working with, gives a set of algebraic equations. And when we take those algebraic equations, we can write them in matrix form like what's shown here. And the matrix is always going to have this shape, or this form, where there will be 2's on the main diagonal and -1's on the diagonal that's one off of the main diagonal. And then the rest of the matrix is just filled with zeros. So for 9 grid cells, or if the wall is divided into 9 grid cells, we end up with a 7 by 7 matrix. That matrix multiplied by the vector of temperatures. These are the temperatures at the grid cell points. And the right-hand side is composed of this. We can see most of the right-hand side is just the ratio of Q over K multiplied by delta X squared. The two endpoints have got temperatures on the left-hand side wall and temperature on the right-hand side wall in the expression. And as I said, if there are 9 grid cells, then the matrix is 7 by 7. If there's 6 grid cells, it'd be 4 by 4. There's always 2 less number of, or the matrix is always going to be rank 2 less than the number of grid cells. We take that matrix, we call it A, we can call it B, D. In this case, I call the matrix D multiplied by the temperatures T is equal to F. If I invert the matrix D, I multiply by the right-hand side, it gives me the vector of temperatures. So now what we'll do is we'll go through this for the example, for the assignment. And in the assignment, I asked you to take the wall, which has a thickness equal to 1.0 meter, temperature 100 on the left-hand side, temperature 20 on the right-hand side. This is the thermal conductivity. And in the example, I'll use Q is equal to 40. For the assignment, I asked you to use delta X equal to 0.1. I'm going to, that would mean that there are 10 grid cells. The matrix would be 8 by 8 as a result. I'm going to do it with 7 grid cells. So delta X would just be equal to, a 1 divided by 7. So we'll do it for this case, where here's the wall. It has width equal to 2 times L. The delta X, if I have 7 grid cells, would just be equal to 2L divided by 7. So let's look at MATLAB. First, we want to formulate the matrix A. And I can do that by the commands that we've used before. It's going to be, because there are 7 grid cells, the matrix will be rank 5. So there'll be it'll be a 5 by 5 matrix. Okay. I made a mistake there. I think I typed something wrong. A is equal to zeros of, yeah, I put a 50 in there. So I'm going to go in here, I'm going to delete this. Start over again. A. So here's A. Now we know that the main diagonal of this matrix, which currently is 0, is going to have 2's in it, and then the 2 off diagonal terms will be -1. So I can start this off by saying that A of 1, 1 is equal to 2. A of 1, 2 is equal to -1. So you can see I've already started this. I'm going to modify, do the last row of the matrix. So you can see that now I'm just going to have to fill in the internal points here. If this matrix was, if there were 1,000 grid cells, obviously there would be a lot more terms that would show up on the screen here, but the first 2 cells in the first row would look like this, and the last 2 cells in the last row would look like this, regardless of how many grid cells we'd be using. So now to fill in, I'm going to use the for command. So what we're going to do is we're going to go from row 2 through row 4, and I'm going to fill in Alright, so with that simple loop, I've now filled in the main diagonal with 2's, the ones that were 0 before, and the off-diagonal terms all have -1's. We had almost all 0's previously. That's my A matrix. The B matrix has got, if we go back to the form of the matrix, or the vector in this case. So just to reiterate, now I have my 5 by 5 matrix that has this form with 2's on the main diagonal and -1's on the off diagonal. The B vector is the product of delta x squared times these q over k's. And the only terms, basically all these will be repeated for all rows of the B vector. The only thing is that the first row will have a T, the temperature on the left-hand side of the wall, on the left-hand wall of the left-hand side of the wall, and then the temperature on the right-hand side of the wall would be added in there. So we'll go through that procedure. We can basically set up the B matrix with just the Q over K multiplied by delta x squared to start with, and then we can just add to the first row and the last row the temperatures that are corresponding to the wall temperatures. So to do this, first what I'm going to do is I'm going to define my delta x. Delta x is equal to 1 meter divided by 7, because there are 7 grid cells. And we use delta x squared, which I'll call dx2. Okay, so there's the value of delta x squared. Also want to define the q and the k. Q is equal to 40. K is equal to 0.5. We also need to define the temperature on the left-hand side, which is 100, and temperature on the right-hand side, which was equal to 20. I think now I have all the parameters defined. We can set up an initial vector B is just 1's of 1 by 5. Okay, so there's that, and B is equal to B prime. Gives me the vector. B is equal to B times dx2, which is dx squared times q divided by k. Alright, so there's the B vector without the temperatures on the boundaries being specified, or being put in there. Here, B of 1 is going to be equal to B of 1 plus T1 on TL. And B of 2 is going to be equal to B of 2, or sorry, B of 5 is going to be equal to B of 5 plus TR. Alright, so this is my B vector, which corresponds to this vector that we see in the handout. Alright, so now we've got the A matrix, we've got the B vector, we invert the A matrix. I'll call that A inverse is equal to inverse of A. Alright, there's the inverse of matrix A. And now I can calculate temperatures. T is equal to just A inverse times B. Alright, so there's the temperatures that are in there. This first temperature, 90.74 degrees. be the one for grid cell 2. 37.41 degrees would be for grid cell number 6 in our formulation. So we have 2 through 6 calculated, the temperatures for these grid cells 2 through 6. Temperature at node 1 is, or for cell 1 is equal to 100. Temperature for cell number 7 is equal to 20. So in order for us to be able to plot this, I want to be able to create a vector that includes the temperatures on the boundaries. So what I'm going to do is I'm going to use a for loop to do that. I'm going to say I is equal to 2 is equal to 1 through 5, and I'm going to create a new vector called TB, and we're going to use the vector of temperatures that we calculated above. So here TB is got right now TB of 2 is equal to the temperature we calculated in the original vector. This is for 90.74 would be for grid cell 2. 37.41 would be for grid cell number 6. The 0 that appears there is a placeholder for the temperature on the left-hand boundary. So we'll say TB of 1 is equal to 100. And we also need a temperature for node 7. Okay, so now we have the complete vector TB, which is the temperatures at all the grid cells. The ones we calculated with the matrix goes all the TB of 2 through TB of 6, and then the boundary points are TB of 1 and TB of 7. We also need to have the locations of the grid cells, and here we'll have the vector x, and the first grid cell, the center of the first grid cell is just going to be at the position delta x over 2. And this is going to go by a increment delta x, and it'll go all the way up through delta x over 2. I'll say 1 minus delta x over 2. So this is the vector for the grid cell. This basically to illustrate that, the point at the center of the grid cell is gives you the x location of it. And this first one appears at 1/2 of a grid cell over from the left-hand side, and this one here, number 7, appears at 1/2 of the distance from the other wall. So the first grid cell, center of the grid cell is at 0.0714. The last one is at 0.9286. So now we can plot these. And that's what that would look like. If I wanted to, I could go through and I could just change the value of Q and recalculate the vector B. I've already inverted the matrix A. That doesn't change if I change the value of Q, or if I change the value of K, if I change TL, if I change DR. None of those will affect the vector A, or the matrix A. I've already inverted it, so the only thing that would be affected would be the vector B. And if I just reformulate the vector B, I'd be able to recalculate the temperatures and formulate them so that I can, through the same procedure, to be able to plot them.